emissions by major and other gases have been converted into the equivalent global warming potential. So what we see here, the CO2 emissions from fossil fuel is the biggest or largest contributor contributing more than 62%. Then CO2 emissions because of land use change like deforestation, CO2 emissions because of chemicals. So if you add all these three CO2 emissions, sources, we can get like roughly 76%, and then 16% is from methane. So it becomes like 76 plus 16, 92%, and then rest are HFCs and CFCs and N2, right? So fossil fuel emission has been the biggest cause of this greenhouse rise in the greenhouse gases. But there are other factors like land use change and CO2 emissions from chemicals, or the permafrost thawing, or the CS4 or methane emissions from the agriculture sector. So this gives us, in a sense, that what are the major sources that are causing the rise in greenhouse gases emissions that we have seen in the previous slide, suggesting that the greenhouse gases emissions from the anthropogenic factors is the biggest factor behind the change in or rise in temperature in last 100 or 50 or so years. The second is that what activities do we do that basically emit greenhouse gases? So this is the partition, like 25% comes from the electricity generation, 24% comes from food and land use. So we can see that food and land use change contribute almost as much as the electricity generation. And then 14% from transportation, 21% from industry. So if we get the number like electricity, food and land use and industry contribute more than 20% of the total greenhouse gas emissions. And then there are some other factors like buildings and other energy sources, 6% and 10%. So what we can learn from this figure is that food habits and land use change contribute as much as electricity generation to greenhouse gas emissions. And now when we emit CO2 to atmosphere, what happens basically? Where does it go and how it is partitioned? So that tells us what happens to greenhouse gases emissions. So long-term increase in the atmospheric CO2. So 45% remains in the atmosphere, and that causes like long-term increase in GHGs, or what we have seen like why CO2 concentration in atmosphere has become 416 ppm today, comparing to it has never reached above 300 ppm historically, even if you go to 800,000 years back in the Earth's history, right? So 45% remains in the atmosphere, and but 55% roughly or 54% comes back, and that can be absorbed by land-based sinks of carbon dioxide like forest, and then ocean-based sinks of carbon dioxide. But both of these have its own limitations, right? So ocean acidification can reduce the capacity to absorb CO2. So the capacity as sink can be reduced in future if we keep increasing the greenhouse gases in the atmosphere. So what we have to basically learn from this figure that whatever greenhouse gases are emitted, 45% remain in the atmosphere, and these are the major causes, basically why we are witnessing the rise in temperature and problem of climate change. So this is basically a figure to give you an idea that how if you get the 1884 temperature with respect to 1951 to 1980 average, how the 1884 temperature will look like. And if you see the scale, you will see the temperature was like 2 degrees, 3 degrees, or at least more than 1 degree cooler at majority of places in the Earth. Okay. Now, if you compare that figure with 2019 relative to 1951 to 1980 mean, this is the situation, and you see that temperature in the northern latitudes, especially Arctic or in Siberia, has increased significantly more than 2 degrees or more than 5 degrees Celsius. So we have now we know that why it has happened and what it can cause. So I don't know. I mean, many of you have heard this news very recently. Came like in Siberia, the temperature reached more than 38 degrees Celsius. I think it's around 22nd of June, and it happened first time in the history. So in the entire record of last many years, temperature did not cross that limit. So 38 degree in Siberia, and it is now causing forest fire and different other kind of implications like dying of permafrost and so forth. So now, I mean, now up to now, we know that what are the climate change, what are the factors of climate change, why climate change is anthropogenic, why climate change is a problem, right? Why it doesn't make sense to compare it with the rise in temperature or rise in CO2 concentration historically, going back to 400,000 years. So now we will discuss like what are the climate projections and what we can get from climate projections and why those are important. So IPCC released a summary for policymakers from it's a special report, and I guess it came around 2 to 3 years back, and where they sort of attributed that human activities caused approximately 1 degree Celsius global warming from the pre-industrial level, and that's what we have seen in the previous slides, right? Not only that, global warming is likely to reach 1.5 degree between 2030 to 2050 if we continue the greenhouse gases emissions with the current rate. So the temperature will become 1.5 degree warmer than the pre-industrial level by 2030, and 2030 is not far away. It's just 10 years from now, right? Now, what are the implications of these changes? The implications are that because of this rise in temperature, intensity and frequency of climate and extreme weather events have increased. And there is a large degree of basically mean temperature in over land and oceans has increased in most of the places. So as hot extremes, extreme hot days or extreme warm nights have increased, very high confidence in that. And there is also a medium degree of confidence that there has been increase in heavy rainfall events and the frequency of droughts in some parts of the globe. So CMIP 6 is basically there now. We are going to have the CMIP 6 projections very soon, right? And so what this slide tells us that what are the different scenarios and what do they mean in terms of projections. Now, why do we want projections? We want projections to understand that if we go with certain scenario, how much temperature change will happen and how that may affect our other sectors in terms of impacts like agriculture, forestry, or systems in rivers, and so basically there are different number of scenarios have been used basically in CMIP 6, and you can see going from green color to dark red colors and green colors. So like if we follow the strong mitigation, so by 2100 if we follow the strong mitigation, we may see temperature rise not more than 1.5 degree or between 1.5 to 2 degrees. And that will happen when we follow very strong mitigation, right? If we don't follow mitigation, then there are other scenarios like SSP 3.7, SSP 3.4, and SSP 5.5. So if we go like worst case scenario, we don't do any mitigation, we can reach like we can see as high as more than 4 degree or 4.5 degree rise in global mean temperature by the end of 21st century. Okay, so CMIP-6 has involved SSP, which is shared socioeconomic pathways, and those are basically considering sustainability, SSP-1, and SSP-5 is fossil fuel-based development. So we don't cut the use of fossil fuel, and we generate our electricity mostly from the fossil fuel. And then what would be the shared socioeconomic pathway? And then it is combined with the radiative forcing like 8.5. That means there will be an increase of 8.5 watt per meter square in radiative forcing by the end of 21st. So they also provided like different, if you see in this right side of your slide in the water, there are also like different distribution is given of different greenhouse gases or radiative forcings. You can see that CO2 is the major player along with CH4, but there are some forcings like aerosols that act in negative. So industrial aerosols basically reduce the temperature, right? And that's what we have seen in the slide where we discuss the different radiative forcings and why the climate changes and anthropogenic. So these are the scenarios basically developed by CMIP-6. IPCC is coming with the report, I think, early next year or by the end of this year. So we can use these scenarios for impact assessment. Remember, these scenarios are projections. These are not predictions. Projections mean if you consider this scenario, how much temperature rise can happen and how that temperature rise will translate into the impacts in different sectors. Right? Now, if I ask this, like which scenario would be the most suitable for our country? I mean, we have to look the trajectory of last 30, 40 years that which scenario we have been following and what is the probability or possibility that India is going between these two scenarios or these three scenarios. And based on that, basically we can generate projections and do the impact assessment. So, I mean, we have in our lab, we have downloaded this data and looked at basically that what are the different projections suggest in terms of rainfall or precipitation in different scenarios. And you can see that this is for South Asia, but you can also take a look at the Indian part that we are going to go into wetter and warmer climate. And temperature can be as high as between 3 to 4 degrees by the end of century in the worst case scenario. Right? So what happens when you change the mean temperature or change the variability of the climate system? So if you can change the means, if you change the mean temperature, you will get more and more extremes. As you can see, the probability of occurrence of extreme events like hot weather or recorded hot days or warm nights will increase. If you increase the variability, you may also see the both kind of events occurring more frequently, like extreme cold events as well as extreme hot events. So we can basically see that how the variability and mean is going to change from these projections that are given by CMIP-6 or IPCC. And then we identify that how much increase in extreme weather events is caused by change in mean in temperature or by the change in variability in temperature, right? Now I will go to impact. So we have covered two parts. First was the basics of climate change, and the second was climate change projections. So now we are moving into climate change impacts, and we know that if temperature, rainfall changes or other climate variable changes, there will be impact in different sectors, starting from agriculture, water resources, public health, electricity demands, or electricity generation from hydropower, right? So this is this slide that gives you basically an idea that what kind of effects we can see because of the climate change in temperature, rainfall, and sea level rise on health, agriculture, forest, water resources, coastal areas, and so on and so forth. So now I will discuss some of our work that basically gives us an idea that what basically climate change projects and what do climate change projections mean for India, and I will discuss very quickly because of the lack of the time. So basically, if you increase the temperature 2 degrees from the pre-industrial level, there could be 7 times more hottest summer that we have observed in the history. So here we looked at different climate regions. We identified the hottest summer, how hot occurred in last 60 or 70 years, and then we estimated the probability of these hottest summers in the occurrence in the 2-degree warmer world. So if you change the temperature 2-degree global mean temperature from the pre-industrial level, how often these hottest summer that occurred only once in 70 years will occur. And we found like there will be roughly minimum 7-fold rise. In some climatic zones, it may be more than 7-fold, maybe 10-fold rise of these. So they will occur more frequently. So that is basically very robust result when it comes about the extreme hot temperature or hot summers, how they are likely to increase. Now, if you increase the temperature or because of the climate change more than 1.5 or 2 degrees Celsius, there will be a tremendous increase in heat wave exposure in India. And heat wave exposure means if we compare like mega heat waves that occurred in the history, like 1998 heat wave that caused more than 2,000 people mortality, and 2015 heat waves, and you can see in the figures that what are the areas were affected by these 2 heat waves. So what would be the probability of these kind of heat waves occurring if we go into 1.5 or 2 degree warmer world? And we see that there would be considerable increase, and in some areas with some projections it suggests it could be like 10 to 20 times increase of that kind of heat waves by the end of 21st century in the worst case scenario of RCP 8.5. Now, heat waves mostly we use maximum temperature, but the problem with the maximum temperature is that it doesn't account for the nighttime temperature, right? So we looked at in one of our papers that what would happen to concurrent day and nighttime heat waves. So why it is important? Because if nighttime temperatures are cooler or less hot, then we get some relief during the nighttime from the heat. But what are the chances that both day and nighttime concurrent heat waves will occur in India? And that we looked at in the historic past, in the observations also, how these events have increased. And we found that there has been a considerable increase in these concurrent day and nighttime heat waves, and those are likely to increase in the future also. So not only temperature extremes, we are going to witness the droughts or dryness or increased droughts in India under 1.5, 2 or 2.5 degrees Celsius. And in this work, we have shown like that dryness will increase in future. And these are all published papers. So I will share the reference if you want to know more about these. And that will cause basically considerable increase. You can see that how the best GCM suggests the increase in dryness if the temperature goes more than 2 degrees or 2.5 degrees Celsius. And remember that 2 degrees very if we do very strong mitigation, then that is the possibility. Otherwise, it would go beyond 2 degrees Celsius by the end of 21st century. So we also looked at like how hot and dry summer extremes or hot and dry summer monsoon will change in future, and this is also published work. We linked that basically that how the frequency will increase in the future and how it will affect the food production. Right? In India, we have made tremendous progress in increasing the food grain yields or the crop yields, and we have become self-sufficient in terms of food availability or food production. But if we get frequent hot extremes and dry extremes in the future, that have a very serious implications for the food production or agricultural production, right? Okay, so that was about the temperature and droughts or dryness. Now I will focus on the precipitation events. And in this, basically, whether precipitation events have increased, whether those are caused by anthropogenic warming So these are, and what do we mean by increase in precipitation events, whether floods have increased or not in India. So these are the basically a few papers that we have published in the past few years. I will quickly discuss, and once again, if you want to know more, there is a list at the end of these slides. You can always look at. So what we basically studied here, that whether increase in precipitation extremes is caused by anthropogenic warming, because precipitation increase can happen because of climate variability also. So we looked at historical natural as well as historic projections that include the greenhouse gas emissions, and we found out that what is the difference between these two, and that suggested that in historical, which has the greenhouse gas, anthropogenic greenhouse gas emissions, there is a significant increase in the extreme precipitation event. So both daily and multi-day extreme precipitation, remember multi-day extreme precipitation, if rainfall, extreme rainfall continues 2 to 3 days or more, those cause flooding mostly, those are likely to increase in the future as these projections suggest. Basically by the end of 21st century, you can see that in South India or parts of North India also going to witness the increase in extreme precipitation events. So that increase in extreme precipitation will also create flood risk. And I would again highlight that the work on national level flood assessment has not been basically, there is not much around. So we looked at that how floods will change because of rise in temperature, global mean temperature. So we ran our model. We first looked at extreme precipitation events. Those are going to increase in future in different river basins, and multi-day extreme precipitation events like 3-day extreme precipitation events are going to even increase in large numbers in majority of these river basins, and that will create more frequent floods basically in India or the Indian subcontinental river basin. Now you can also see the difference between low emission scenario and high emission scenario, how the frequency of floods is different in these two scenarios. So what does it mean? It means that if we do climate change mitigation and if we limit the global mean temperature below 1.5 or 2 degrees Celsius from the pre-industrial level, we can reduce the flood extremes, or we can reduce the increase in the flood extremes in different river basins in comparison to worst case scenario of RCP 8.5. So that helped us to understand that how important is the climate change mitigation. Right. Not only that, we see more frequently urban floods, and there has been a lot of work on urban floods by different institutes, including IISc Bangalore, Indian Institute of Technology, Bombay. We also looked at that how sub-daily rainfall extremes will change, and that has strong implications for urban flooding. So we looked at cities in India. I think around 50 or so large cities